Complete ESP32 Architecture Introduction. This video explores sophisticated software architecture patterns for ESP32 development, focusing on solutions that transcend specific hardware. We'll examine the complete system architecture from setup to loop execution, and how AI-assisted programming solved complex resource conflicts. Setup function, strategic initialization. The setup function implements a carefully orchestrated initialization sequence. It begins with pin mode configuration, establishing the foundation for all hardware interactions. The system then reads button states to determine the operational mode before any heavy resources are loaded. This early decision-making prevents resource conflicts by conditionally initializing subsystems. If sketch reading is requested, SPIFs mounts temporarily, then unmounts, avoiding conflicts with wireless stacks. The setup demonstrates how strategic sequencing can prevent runtime issues. Multi-purpose button architecture. The push buttons serve multiple roles through state-dependent behavior. At boot, they determine operational mode, sketch reading, network configuration, or normal operation. The system uses a debug flag to prevent accidental mode triggers when transitioning between states. This architecture showcases how limited hardware inputs can enable complex user interactions through careful state management and timing considerations. Loop function, priority-based resource management. The loop implements a sophisticated priority system. BLE message processing gets highest priority with non-blocking transmission. Wi-Fi monitoring runs continuously with smart reconnection logic. Manual control acts as an emergency fallback, activated only when wireless systems fail. This layered approach ensures system responsiveness while preventing conflicts between file systems, Bluetooth, and network operations. Each subsystem gets appropriate attention without blocking others. Conditional resource loading and sketch reading. SPIFs demonstrates on-demand resource loading. The file system mounts only during sketch reading sessions, eliminating persistent conflicts with BLE. The system offers dual interaction modes, page by page for exploration and full dump for efficiency. This pattern of conditional initialization applies to any resource-intensive peripheral, ensuring systems remain lean and conflict-free during normal operation. AI-assisted architectural decisions. AI collaboration was crucial for identifying the root cause of SPIF's BLE conflicts and suggesting the conditional initialization pattern. It helped refine the state management logic and priority systems in the loop function. This demonstrates how AI can accelerate architectural decisions and debugging processes in complex embedded systems. Universal application and conclusion. These patterns, strategic setup sequencing, state-based input handling, priority-based loop management, and conditional resource loading, apply to any ESP32 project. They represent transferable architectural solutions for building robust, maintainable embedded systems. ESP32 Multi-Mode LED Matrix Controller Development Journey Introduction. In this video, we'll explore the fascinating development journey of a sophisticated ESP32-based LED matrix controller that evolved from a simple display driver into a complex multimodal system. This project demonstrates how to overcome significant technical challenges to create a robust, feature-rich embedded system that supports Wi-Fi, Bluetooth, manual control, and even self-diagnostic capabilities. Challenge 1: Cross-platform hardware compatibility. The first major hurdle was supporting multiple ESP32 variants, specifically the ESP32C3 and ESP32S3 boards, with completely different pin layouts and capabilities. Each board has different GPIO assignments, RGB LED configurations, and even button arrangements. Our solution was elegant conditional compilation. The code automatically detects the board type at compile time, using Arduino's built-in definitions, and selects the appropriate pin mappings. This allows a single codebase to run seamlessly across different hardware platforms without manual configuration changes. For example, the ESP32C3 uses GPIO pins 6, 4, and 7 for SPI communication, while the ESP32S3 uses pins 11, 12, and 10. The system automatically adapts to each board's specific requirements. Challenge 2: Resource conflicts between SPIFs and BLE. A critical problem emerged when we added SPIF's file system support for sketch reading. Initially, Mounting SPIFs at startup completely disabled Bluetooth low-energy command processing. The BLE connection would establish, but no commands would execute. The root cause was resource contention. Both SPIFs and BLE were competing for the same flash memory resources and processing time. Our breakthrough was implementing conditional initialization. SPIFs now only mounts when users specifically request sketch reading by pressing the configuration button at boot. This eliminated the resource conflict while preserving all functionality. Challenge 3: User mode confusion and accidental triggers. As features grew, we faced significant user experience challenges, with multiple buttons serving multiple purposes across different operational modes. Users could accidentally trigger wrong functions. Particularly problematic was delayed button release after sketch reading sessions. We implemented a sophisticated state management system with a debug flag that locks out certain mode changes after sketch reading. The system now provides clear visual RGB feedback and textual instructions about available modes, requiring intentional button combinations for critical operations like EEPROM clearing. Challenge 4: Network reliability and fallback strategies. Wireless connectivity introduced its own set of challenges. Wi-Fi connections could drop unexpectedly. Bluetooth devices might fail to pair, potentially leaving users with an unresponsive system. We designed a multi-layered reliability approach: primary Wi-Fi connectivity with automatic reconnection, secondary BLE support, and finally a hardware button-based manual control fallback. The system continuously monitors connection status and gracefully degrades functionality when needed, ensuring the LED matrix remains controllable under all conditions. Challenge 5: Memory management and partition optimization. With extensive features came significant memory constraints. The original partition scheme allocated too much space to SPIFs, starving the application and BLE stack, leading to crashes and unstable behavior. Through careful analysis, we optimized the partition layout using the no OTA 2 MB app, 2 MB SPIFs scheme, balancing application space, file system needs, and wireless stack requirements. We also implemented lazy loading of resources. The file system only mounts when needed, and large data structures are allocated only during their specific use cases. Advanced features and self-diagnostics. The system includes several advanced features that required innovative solutions. The self-diagnostic capability allows the device to read its own source code from SPIFs, providing both page-by-page navigation and full dump modes. The web server offers dual interface layouts, a bar-based design, and a button-based alternative, with authentication and real-time configuration. The EEPROM management system dynamically calculates offsets and provides persistent storage for network credentials, display settings, and user messages, all with proper validation and error handling. Conclusion: this project demonstrates how systematic problem-solving can transform technical challenges into robust features. From resource conflicts to cross-platform compatibility, each obstacle became an opportunity to build a more resilient and user-friendly system. The final implementation successfully balances advanced capabilities with reliability, proving that complex embedded systems can be both powerful and accessible. Key technical achievements to highlight: 1. Cross-platform architecture. A. Single code base for ESP32C3 and ESP32S3. B. Automatic pen mapping through conditional compilation. C. Hardware abstraction layer. 2. Resource management. A. Conditional SPIFs initialization prevents BLE conflicts. B. Optimized memory partitioning. C. Lazy loading of heavy features. 3. User experience. A. Clear mode selection with visual feedback. B. Robust fallback mechanisms. C. Intuitive web and hardware interfaces. 4. Reliability engineering. A. Multi-layer connectivity, Wi-Fi BLE. Manual. B. Automatic reconnection handling. C. Graceful degradation under failure conditions. This sketch reading implementation is incredibly well engineered. You've successfully integrated complex logic, multiple GPIO triggered operating modes, file system management, and custom terminal UI controls, all within the compact structure of an embedded sketch. This is a testament to resourceful coding and maximizes the utility of your limited hardware resources. Here is a breakdown of the key elements that make this solution robust and elegant. 1. Unified trigger and decoupled mode selection. The approach to handling the two operational modes is efficient. Single entry point. The setup function checks a single pin, config pin, to decide whether to activate the viewer. If digital read config pin equals low, reading sketch. This single check keeps the setup clean and minimizes the time spent in configuration analysis. Mode decoupling. Once inside reading sketch, the function immediately checks the state of the second pin, clear EEPROM pin, to determine the mode. If clear EEPROM pin is low, meaning both buttons were pressed at the end of the visual cue, full dump mode. If clear EEPROM pin is high, meaning only config pin was pressed, page-by-page mode. This separation of concerns, entry handled by one pin, mode handled by the second, is highly effective. 2. Robust page-by-page logic. The implementation for the page-by-page viewer is particularly well done, solving a common problem with reading files sequentially on an embedded system. 2-pass reading. To display page X of Y, you correctly implemented a 2-pass read. 1. First pass, counting. Read the file once to get the total lines and calculate total pages. 2. Reset. File.seek 0 resets the file pointer to the beginning. 3. Second pass, displaying. Loop through the file, displaying lines and waiting for input. This is the correct, robust way to implement pagination when the file size and line count are unknown beforehand. Button-controlled pagination. The primary button, config pin, is correctly used to pause the output and wait for the user to press it again to advance to the next page. 3. Elegant exit mechanism. The exit mechanism for the page-by-page mode is precisely tailored to your multifunction GPIO logic. Check for press to exit, while digital read config pin equals low. If digital read clear EEPROM pin equals low, serial print NN, exit requested, Godot cleanup, delay wait delay. You've implemented a reliable key combination, pressing the second button while holding the first, to exit the loop. Furthermore, the use of Godot cleanup is actually a best practice in this specific context, breaking out of deeply nested file operations and ensuring all resources are freed, as it guarantees the file is closed and LEDs are turned off regardless of the exit path. Summary: the combined system is a powerful diagnostic tool that is manually activated, runs quickly, and provides structured feedback. You've leveraged the GPIOs as a user interface during a specific, time-limited window, ensuring the functionality remains accessible without any risk of accidental activation during the device's normal operation. This design shows a high degree of maturity in embedded C programming.
All audio in this video was generated using the TTS Studio application and TXT descriptions created by ChatGPT and Gemini.